Here is the question that I asked at the end of the last part of this lecture. Notice that the person is not inside the system. The changes in chemical energy, and as a result changes in thermal energy, would be happening in the person. And so that's outside the system and shouldn't be included in the energy bar chart. Also notice I helpfully showed you both the force that the person is exerting and the force displacement vector for it. And they're pointing in the same direction, and so the work done by that force must be positive. Also, when you compress a spring, it doesn't lose energy, it gains energy, and so D can't be right. And so the answer is B. If you had some numbers in this problem and were then going to go on and try and calculate something, you would want to convert this energy bar chart into an equation. Let's first just dissect it. It's got an initial energy and a final energy, each of which has several parts. And so our equation would be formed by remembering that the equals sign goes just after the work, right? Because if the work is positive, the final energy is bigger than the initial energy. So you add that work onto the initial energy to get the final energy. And so now I'll just rewrite it with all the symbols in, where I've left out the initial spring energy because it's 0. Another alternative would be to think in terms of changes in energy. So we've seen before that we can draw energy bar charts that are talking about changes of energy. And now when you're doing that with a work, all of the changes of energy have to add up to the total work. And so the equation that you would get out of that would just look like this.
Let me now do an example that illustrates some of the issues that come up around choosing our system. So here is a pail that's being lowered by a rope, and there's a rope brake that's slowing it down. You might not know what I mean by a rope brake. It's something like this or like this that rubs on the rope as the rope passes through it. And so the main point is that the rope brake is eventually bringing the system to rest, and it's doing it by friction, and so thermal energy is produced at the brake, and some of that thermal energy ends up in the rope. So now let me look at 3 different choices of system and how those lead to different conclusions about the system energy, although in the end, everything has to agree. I've noted a few things to start. I've drawn the free body diagram for the pail just to note that the only forces on it are a gravitational force and a force by the rope. And I've also set up my energy bar charts, and the pail is included in my system for all 3 choices. I know the pail is slowing down, and so I know that the change in kinetic energy is negative. Now, the first choice is to include the pail and the Earth in my system. Note that the pail goes down. And so we know the gravitational potential energy is decreasing, and so the change in gravitational potential energy is negative. And that should be everything for the energy in my system. The only other possibility here is a thermal energy. We know that's in the brake and the rope, and those are excluded from the system. But now look at the work done, because we can see that the change in system energy must be negative. Let's make sure that that's what we come up with when we analyze it. The gravitational force is an internal force, and so all we have to worry about is this force that the rope exerts on the pail. That points up and is an external force, but the other thing to notice is that the force displacement points down. And so the external force and the force displacement point in opposite directions. And so, as we expect, because the system energy is decreasing, the work ought to be negative, and everything is adding up correctly and making sense. Now let's look at what happens when I do all the same things, but this time the brake is included in the system. Well, the pail and the Earth are still included in the system, and so the gravitational potential energy has to come out the same way. However, now both of the forces acting on the pail are internal to our system, and so they do no work. The support that is holding the brake must be exerting a force on the brake. However, the point of application of that force doesn't move, and so that force does no work, and so we don't have to worry about it. But now we've included the brake and the rope in the system, and so the thermal energy that collects in those is part of the system now. And so we can see that the system energy can be conserved because there is a positive change in thermal energy, which should offset the loss in the kinetic energy and the gravitational potential energy. Finally, let's look at one more choice. This time we're including the pail and the brake in the system, but not the Earth. The consequence of that is that the gravitational force is now an external force on the system. It acts down, and as before, the force displacement vector also acts down. And so that means that the work done on the system by gravity should be positive. Note that we can't talk about a change in gravitational potential energy because we haven't included the Earth in our system, but we're still accounting for the effects of gravity through the work that the gravitational force does on the system. Once again, the rope and the brake are included in the system, and so we have the thermal energy, and there's a positive change in thermal energy. So let me stress that this has come out looking differently, but if I knew things like the inertia of the pail and the height that it falls through before coming to rest and things like that, I would be able to solve for everything else, and my solution would come out the same no matter which of these choices of system I made. As we've just seen, you can include the Earth in your system or not. Either choice is valid. However, you should make the choice very deliberately and be very clear about what choice you've made, because it'll make a difference to how you carry out your analysis. Remember that any potential energy always depends on relative positions of the objects that are inside the system. And so that's why if the Earth is outside the system, then you can't even define a gravitational potential energy. On the other hand, work always refers to changes of the system energy resulting from external forces. That means if the Earth is inside your system, then the gravitational forces do no work because they're internal forces to your system. So you need to make a choice. Either the Earth is inside your system, in which case you account for effects of gravity by looking at the gravitational potential energy, or the Earth is outside your system, in which case you account for the effects of gravity by calculating the work done by gravitational forces. You can do either one of these. The important point is that you must never do both, because if you do that, you'll be double counting gravity. My preference is usually to put the Earth inside my system if I don't have a reason to do otherwise, and that's just because gravitational potential energies are very easy to write down and to work with. However, there are times, for example, when for some reason your y-axis doesn't point straight up, that you don't want to use gravitational potential energy. Then you'll need to account for gravity using work. And at that point, it becomes important to realize that the point of application of the gravitational force can always be thought of as the center of mass of an object.
The issue of choosing your system determines which forces are external and therefore which forces can do work on the system. So let's look at another example where there are many possible ways to define the system, and I've defined it in a particular way, and let's see if you can get the energy bar chart right. So we have a mass that's hanging from a spring. This is a lot like something that could happen in the lab, although usually in the lab the mass and spring wouldn't be this big. Anyway, a person pulls down on the mass so that the spring stretches more and the mass goes down. And the system is the mass, person, and Earth. Which of these is the most correct energy bar chart?